Continuing with our next lesson, we're going to take a look at systems of linear equations. Systems of linear equations usually set of two lines, two linear equations with two variables, but it can be more than that. It could also be more than two variables. So we have two linear equations listed here. When considered together, they form a system of linear equations. Now, linear equations with two variables, an individual equation with two variables has an infinite number of solutions. It's any and every point that we can find on that line. Now, when we take two linear equations, a solution to that system would be any point or points that satisfy both equations. So looking to the graph on the right, what ordered pair is a solution to both equations? We're looking for what ordered pair is on both lines. Well, the only point that exists on both lines is this point right here, which is the point 4, 1. So the solution to this system is the ordered pair 4, 1, because that is called the intersection of the two equations. Now we're going to start by covering the first of two methods other than graphing that we can algebraically solve for a system of equations, and that is the process of substitution. First step is we want to isolate the two variables of one of the equations. Which one we isolate, it does not matter. It is up to our discretion to pick the one that we think is probably easiest. Next, we want to go ahead and substitute the expression that is equal to the isolated variable into the other equation. We should end up with an equation with only one variable after we do this. Then we can go ahead and solve for the variable that we have. And then once we have our first variable, we can actually plug it into one of the original equations to solve for the other variable. And it does not matter which equation we use. Substitution works best when we have a variable that's already isolated or easy to get isolated. When we look at our first system here, we see that x is already by itself and that it equals 2y. In order for an equation or a point to be a solution to the system, it is one where the x and the y values are the same. Well, if x in our first equation equals 2y, x in the second equation also has to equal 2y, and that's where the substitution comes in. We can replace the 2y in the second equation with the x in, or the x in the first equation with 2y in the equation. And so we substitute, and then from here we just solve. We can combine like terms, we can divide coefficients, and once we get our value for y, we can go ahead and plug it into either of the original equations. It does not matter which one. I'm going to choose this one because it seems the easiest, as we end up getting a value of 2. So our solution is 2, 1. Next, we have another one where the equation is already isolated for y, so we can go ahead and substitute it in for the y value over here, giving us 4x plus 3x minus 1 equals -8. Combine like terms. We can subtract constants, divide coefficients, and then we go and substitute into an original equation. For example, we can go ahead and take 4x and substitute in the 1. Y, and y equals -4. Okay, so we have our solution as -1, -4. Now, if we don't have a variable already isolated, oftentimes we can easily get one by itself. Notice how this x does not have a coefficient, so all we have to do to get it by itself is add the other variable term to the opposite side of our equation, giving us x equals 2y minus 2. And now we can go ahead and substitute that in for x on this side. So 7 times 2y minus 2 is 3y equals 19. Distributive property. Combining like terms. I'm going to go ahead and bring this up here. We will subtract constants, or actually I guess add this case, divide by coefficients, and then we substitute back in to one of the original equations. And we get our solution of 4, 3.